Hello and welcome to another WJEC A level physics question. This is from Unit 1 in May 2013. It was question 2. It's an electricity question which is nowadays on Unit 2. Question starts by asking us that when a quantity of charge flows into a junction in a circuit, an equal quantity must flow out again. In this way, the flow of charge is conserved in any circuit. And what name do we give to the rate of flow of charge? So this is just testing that we know the definition of current, but in reverse. Usually they ask us what's the definition of current, and we would say rate of flow of charge. If we apply the conservation law to the junction P in the following diagram, well, we can see that there's 1 amp going into the junction. Here, notice the direction of the arrow, and there's a total of 4, 6, 7 amps leaving the junction. So the missing current must be 6 amps, so that we have a total of 7 amps in and 7 amps out. Next, we're given a circuit where we have two sort of parallel combinations of resistors connected in series with each other, and we've got to find the total resistance of the whole circuit when the switches are closed. So if we look at the section XY, then we can use the fact that resistors in parallel add in reciprocal. So 1 over R for XY is going to be 1 over 12 plus 1 over 6, which we can combine together with a common denominator of 12 to give 3 over 12. And that means the resistance between X and Y is 12 over 3, or 4 ohms. Similarly, the resistance between Y and Z is going to be 1 over 3 plus 1 over 6, which will be 3 over 6. And the resistance between Y and Z will be 2 ohms. That means that the total resistance, just call it R total, is 4 plus 2, or 6 ohms. For the next part of the question, we've got to determine the PD between X and Y and also the PD between Y and Z when both of the switches are closed. There's various ways of doing this. One way, for example, would be to realise that the original circuit simplifies down to a 12 volt supply connected to a 6 ohm resistor, and hence that the current in the circuit would be 12 over 6, 2 amps. Then we could apply V equals I times R. The resistance between X and Y is 4 ohms, so the PD between X and Y would be 2 times 4, which is 8 volts, and the PD between Y and Z would be 2 times 2, which is 4 volts, adding up to the 12 volts that we've got. Another way that we can do it, and the way that I'm going to do it here, is just to consider ratios of resistances. Between X and Y we've got 4 ohms, and between Y and Z we've got 2 ohms. That's a ratio of 2 to 1, which means that the potential difference of 12 volts across the whole circuit splits in a ratio of 2 to the 1. Hence we can say that the PD between X and Y is going to be 2/3 of 12, which is 8 volts, and the potential difference between Y and Z will be 1/3 of 12, which is 4 volts. Any acceptable method is fine here. Now the reason why I've decided to do it the ratio way is because of the next part of the question, which says, what would your answers to be? Would they differ, if at all, with both switches open, and to explain the answer? So with both switches open, what we've got here is that between X and Y we've got 6 ohms, and between Y and Z we've got 3 ohms. And that again is still a ratio of 2 to 1. 6 to 3 is the same as 2 to 1. So because the ratio of the resistances doesn't change, the ratio of the potential differences doesn't change either. So we'll simply say here that the PDs won't change, since the ratio of the ratio of resistances is unchanged. For the next part of the question, we're asked to determine the switch settings that would allow a current of 1.5 amps to flow through the cell. So let's work out what resistance we would need for that to happen. So still a 12 volt supply with a current of 1.5 amps. That means we need a total of 8 ohms. If we go back to the original circuit, the way that we're going to get that is to leave S1 open so that between X and Y we've got 6 ohms, and close the switch between Y and Z so that we get the 2 ohms there. Then we've got to determine the power in the switch when both circuits are open. Well, we've got a bunch of formulae that we can use for electrical power, but why not just use P equals V squared over R here? Because we know what V is, it's definitely 12 volts, and with both switches open, we have a total resistance of 6 plus 3, 9 ohms. So we have 12 squared, 144, divided by 9, which is exactly 16 watts. Finally, determine the switch settings that allow the maximum power to be developed in the circuit and justify your answer. Well, a trial and error method works, where we could look at each part of each combination of switches and work out the power in each case, but a much neater method is to look at that equation again, P equals V squared over R. Because V is constant, V doesn't change. It's always 12 volts for the whole circuit there. Therefore, we can say that the power is inversely proportional to the resistance, and hence we need the smallest resistance to get the biggest power. If we look at all the different possibilities, we can have 6 and 3 with both switches open. We can have 6 and 2 with this one open and this one closed. We can have 4 and 3 with this one closed and this one open, but the lowest resistance will be when we have both switches closed, giving us a 4 and 2. There's no need to actually calculate that power, but if we wanted to do it for completeness, we can just use V squared over R again. So we've got 144 over a total of 6, giving us a power of 24 watts. So thank you very much for listening. Please remember to like and subscribe, and don't be afraid to add comments below. Goodbye.